Okay, now it's my absolute pleasure to introduce our invited speaker for the afternoon. It's Professor Behnam Jafarpour. Behnam is a professor of chemical engineering and material science at the University of Southern California, USC. He also has joint appointments in electrical and computer engineering and civil and environmental engineering. At USC, he leads the Subsurface Energy and Environmental Systems Lab and also co-directs the Advanced Reservoir Characterization and Forecasting Center. Behnam's research is at the interface of system science, data science, and computational geoscience. His work integrates advanced system theoretical principles and modern data science algorithms with modeling and prediction for effective characterization, forecasting, and management of flow and transport processes in subsurface systems. And I think you'll see a bit of all of those in his talk this afternoon. So, Behnam, the floor is yours.
Thank you so much, Mike, for the introduction. Good afternoon, everyone, and thanks for coming to the presentation. I would like to begin by thanking InterPore for giving me this opportunity to come and share some of our research work with you. So my lab focuses on developing algorithms and methods for characterization and forecasting and optimization of subsurface energy resources. And these are some of the applications that we work on. But primarily in more recent years, we've been focusing on the use of data science in developing improved methodologies for workflows that I'll talk about briefly in the next slide. So if you look at decision-making process for managing subsurface reservoirs, you see a few loops, iterative loops for basically developing models, updating models, uncertainty quantification, and as well as field development decisions, performance optimization, and risk mitigation. So the focus of our research has recently been in leveraging AI and deep learning in particular to see how we can improve some of these workflows. For today, I'll be focusing on model updating as a specific example of some of the things that we work on. So a lot of effort goes into building subsurface models, but once we begin to see some dynamic performance data, we realize that the models we develop are not necessarily aligned with the data that we observe in the field. And that creates a requirement to maintain these models up to date by bringing data and incorporating data into these models. And that is traditionally been viewed as a challenging inverse problem. What you see here is basically an illustration of on the top of a forward problem where you have a model that is developed to simulate the behavior of a typical reservoir. In this case, this is a valve model shared by BP. And the idea is, by doing that, we want to see what is the performance of this system and hopefully be able to control and optimize the behavior of our system. Our focus is really on the bottom, where we try to look at the feedback that we receive from the field and try to see how we can actually make our model more consistent so that we can improve our prediction. And those predictions go into a similar workflow for optimization of our controls and decisions. A very simple illustration to show how model updating typically is done, and it's a traditional way, is we start by what we see here on the top left, if I can use this, yes, as a given model. And we use that in our, within a simulation model to predict the expected data that we see in the field. And typically we see a mismatch. And this whole iterative loop is designed to update this model in order to match the data that we see in the field. So a couple of observations here that we need to keep in mind in dealing with these problems. One is that the model cannot be updated any way we want. We have to respect the geology. We have to respect the expected heterogeneity in the field. And sometimes we deal with very complex non-Gaussian patterns that are hard to describe mathematically. The other requirement and complication that we have in this problem is the mismatch between the resolution of the data with the resolution of the models that we inherit. I say inherit because typically these models are developed for forward simulation, and we inherit those traditionally for our inverse modeling. But the description is really doesn't have the or have too much resolution for the kind of data that we typically collect and use for inverse modeling. So traditionally, to deal with these challenges, and here's an example showing the type of data. For example, in this case, 5 wells are located in different locations throughout the field, and these are the response data that you receive. The idea is to update this model, and this is just one layer of the model. Generally, we have many of these layers on top of each other, stacked on top of each other. So that having this kind of resolution to characterize is not going to be a good start. So what people have traditionally done in the literature is to try to reduce the dimensionality of the problem, of the parameter space. And fortunately, because we are dealing with geology, there's a lot of correlation that exists in geological formations. And that lends itself to dimensionality reduction by getting rid of some of the correlation structure. So in this example, basically you can see that if you want to reduce this problem very aggressively, you can end up having very few parameters for different zones that capture the geological kind of or heterogeneity that you see in the field. There are also more sophisticated approaches that allow you to do that in a mathematically more advanced kind of fashion. So I'll show you a perspective on how this dimensionality reduction is typically done very quickly. And this is basically a perspective from image processing kind of view. We can actually reduce dimensionality by looking at linear expansions, where we actually write the high dimensional model as a linear combination of a finite number of basis images, each of them with a coefficient or weight in front of them. And the idea is that those correlation structures are embedded into our basis functions, so we don't have to deal with those. What we actually do during the solution of the inverse problem, we actually try to adjust the weights in order to reproduce the kind of patterns that the data is consistent with. Now, the key question here is that how do you generate, where do these basis components come from? From image processing literature, we do have actually quite a few powerful compression techniques that we use on our daily basis on our phone and computers. These are data-independent transforms, including Fourier-based transform, wavelet-based transform, and some generalization of that for unstructured models. And what I come back to talk about later is this encoder-decoder architecture that exists actually in wavelet transforms, which is very well connected to the deep learning models that I'll talk about. So we can actually develop basis functions that are data-dependent, that have geological patterns in them, and there are actually a series of techniques that people have developed to actually solve this kind of problem. As a result, you get more specialized basis images for the particular type of patterns that you have in your problem. Now, if you pick this approach, then you'll end up basically parameterizing your high-dimensional model using very few basis functions and very few a low-dimensional representation of the coefficients. The idea now is in updating this model, we have a low-dimensional set of coefficients that we can update, and those coefficients make adjustment to the high-dimensional problem that we have in the original domain. And this has been used quite extensively in the literature. Now, What we're trying to do, we're trying to see if we can address some of the deficiencies of these existing methods by leveraging AI and deep learning in this case. And basically, because we're dealing with images, the methods that we use for these particular applications are convolutional neural networks, which are very widely used for imaging applications. These are very powerful for detecting local patterns, which we find in natural images, including geological images. And basically, compared to fully connected neural network, you have far fewer weights to train during training. And the key difference here with wavelets that also use filtering is that we use a lot more filters here. And those filters are adapted to the training data that we have. Unlike wavelets, where the filters are pre-designed and you don't work with too many of them, maybe a few. So these are the building blocks, pretty much textbook material, looking at convolutional operation where you scan images using basically a small filter sizes to extract local features and store them and use them for later on for prediction. We introduce nonlinearity through nonlinear activations. And dimensionality reduction is achieved through pooling and subsampling. And at the end, a lot of these filters are used across multiple layers to detect different scales of information and correlation patterns. So here is an architecture for dimensionality reduction, which is very popular, autoencoder, where you basically use a combination of encoder-decoder. The encoder is used to map high-dimensional inputs into a low-dimensional representation, basically called latent space. And from there, we have a decoder that does the opposite and maps the low-dimensional representation back to the high-dimensional original domain. So if we actually do this successfully, then the decoder will provide the parameterization that we need, because now we can actually use very low-dimensional samples that can be mapped into high-dimensional original images that we have, and then we can update and operate in the low-dimensional latent spaces in order to do model updating. However, in order to do that, the low-dimensional latent space should be well-behaved. And by that, what we mean really is the ability for the low-dimensional latent space, 2 points that are closed should also provide closed representation in the original domain. And also, any sample you pick from here within the range of data that you have should actually give you a meaningful output. So that's basically, these two conditions are satisfied through a kind of expanded version or a variation of this called variational autoencoder, which is what we primarily use, and a lot of the things that I talk about are based on it. There are other implementations for low-dimensional representation, generative models, et cetera, but most of what I present today is based on this. Now, I'm going to show you 3 different applications, how we can use these kind of architectures in order to do inverse modeling in a latent space. First one is a very simple parameterization, which is traditionally done, except that we actually take advantage of the decoder of these architectures to do dimensionality reduction. The second one is what we call latent space inversion, where we actually bring the data also into the latent space, and we do the inversion within a joint latent representation of both data and the parameters. And the third one is latent space, what we call latent space data assimilation, where we actually try to implement existing type of updates for data assimilation, but we do that in the latent space because the latent space has some very useful properties that are consistent with the assumptions of those updated schemes. So very quickly, the parameterization, going back to this loop for model updating, now we have a deep learning model here with a low-dimensional representation, and this decoder is allowing us to create patterns that are, in terms of a spatial connectivity, consistent with our prior data. And also, it would allow us to basically update the model to kind of create patterns that can match the data. I'll show you one of the important properties that we kind of exploited from deep learning models is their robustness. Quite robust to having very diverse pattern from geological kind of conceptual geological models that can be incorporated into these architectures, and without affecting their performance. And that was something that was quite interesting for us to see, because typically in traditional low-rank representation techniques, diversity of your data ends up degrading the performance of your representation. But this is something, because there are so many filters that are incorporated into these architectures, they do a very nice job of detecting different patterns without really, without the performance going down. So here's an example from one of our papers where we actually have fluvial channels going in very different directions. So for example, if you run a PCA on this, which we've done, you actually don't get very good results. The architectures that you see in here tend to kind of be aggregated, which is not what you want. So this is a pumping test that we ran. This is basically the inversion iterations for when we have one single scenario of this, so we don't have diversity, versus when we have multiple scenarios, where we have actually patterns that are quite diverse. And what we see is that the VAE that we use here is not affected by the diversity, but on the other hand, the traditional methods such as PCA are affected negatively by introducing diversity. Now, this was a very simple approach that we just replaced existing parameterization with the decoder. Now we actually want to come up with architectures that would allow us to do the inversion in the latent space, and that's what we call latent space inversion. So the idea is that similar kind of autoencoder architecture that we have, we can actually have that also for the data space, and we can build a regression model in the latent space between data and models, latent spaces. So that's basically the idea. Now, another illustration here is that you have basically your input models, and the autoencoder is used to kind of give you a low dimensional representation for that. And then the data, you do the same thing. Now, you can actually do a mapping in either direction. If you do the mapping from the latent space of models to data, we're basically generating a predictive model. And that predictive model I'll show you in the ensemble kind of data assimilation. We actually use that. If you go in the other direction, what you're effectively doing in the latent space is really solving an inverse problem. And a nice thing in here is that once you train a model like this, you can actually do inversion pretty much instantly. So the architecture that we put together for that is a joint architecture that does latent space identification for both data and parameter space at the same time, and in addition to the regression model that connects the two. So we actually jointly train using data from geological data or realizations of the parameters of our models, as well as the response data that we collect through the simulators. And after training this, one of the interesting points that is quite different from the parameterization through the traditional approaches is that now through this training process, the latent space that we identify for the model is actually informed by the data too, which is something that doesn't happen in the traditional parameterization techniques, because we just use the samples from the parameters in order to do model reduction. Whereas in this case, because this is joined jointly, the model is actually informed of the physics too, informed of the dynamics or the data that is supposed to kind of represent. So in that sense, it's quite a kind of a different aspect to these kind of architectures. Here's another illustration showing basically the data through the encoder is assuming the training is complete now. Goes to the latent space for the data. The same thing happens on the model side. There's a decoder in this side. So this is a latent space representation for the parameters, latent space representation for the data, and this is a regression model. And basically, if you go in this direction, you can actually do the inversion. Let me show you a few examples. So here is a Gaussian example. Again, you can see that in terms of geology, we are now freely allowing the correlation structures to be very different in terms of both anisotropy and also correlation lengths. Also on the right-hand side, you'll see that we have fluvial patterns. Again, we are allowing them to have different directionality because now we are not worried about these methods are capable of actually handling those. So we don't have to worry about performance going down. I'll show you the reconstruction results using very limited data from 4 wells. These are some examples showing reference cases and the corresponding reconstructed maps. And for the fluvial models, which are a lot more challenging, you'll see that we get very consistent results. Some of these losses are natural because of the way the objective function of our architecture is operating, producing a smooth, continuous result as opposed to discrete. And we applied this to three-dimensional problems. Again, you can see that the geology could be, these are different scenarios for geology for training. And what I'm showing in here is that this is a kind of a reference model, and this is a reconstructed model that, given that we have very few data points, the performance has been quite promising. Now, let me switch to the last part, which is the latent space data assimilation. Another application of these kind of latent space representation is performing data assimilation in the latent domain. And what happens here is because the latent domain has certain properties, including Gaussianity, typical assumption applied to the latent domain, as well as some of the nonlinearity is captured by the encoder and decoder. So in the latent space, the nonlinearity is expected to significantly decrease. So these kind of updated schemes for, let's say, E and KF that rely on assumptions of linearity and Gaussianity could lend themselves to these kind of latent space representation. So that's what we are trying to take advantage of and implement these schemes in the latent domain. So again, similar architectures here. They observe that basically the response data as well as the maps of the realization maps that go into our models are first encoded into their latent space. The same thing happens on the other side for the decoder. Now, the data assimilation is taking place in the middle, where we have latent space representation for the model and the data. Now you can see the direction we are moving. Unlike the previous version, the direction is from the model to the data, which means we are trying to do prediction because E and KF had 2 steps, a forecast and an update. And for that forecast, we are actually implementing that in the latent space through this regression model that we have. So with this, once this is trained, we actually, so this is the architecture that we use for the training, which include 2 tasks, as I said, a regression model for prediction, as well as a model reduction to generate the low-dimensional latent representation. So this is the illustration showing how this is done after the model is trained. The E and KF update is taking place. In this case, we apply ensemble smoother with multiple data assimilation, which is very commonly used. We are doing the iteration of that within the latent space, where the prediction and update are done both in the low-dimensional applied to ZM and VD. So let me, so these are basically showing different iterations of that. So I'll show you the last example here, and then I can conclude the talk. So here's an example of that Wolf model, and these are the initial model that we started with. This is the scheme that we use for model updating. And these are some of the updated models that we have based on very limited data that we collect from the field. And if you look at the predictions and data match from the models, the performance has been quite promising. So these are some of the kind of early work that we've been doing, and currently we are focusing on how we can actually generalize these models. There's a lot of talks about physics-informed modeling, and that can help us deal with some of the data limitations that might exist in our applications. With that, I'll just conclude by basically pointing out that these kind of architectures are quite powerful for model reduction, dimensionality reduction. They're also very versatile and very flexible to put together for a specific purpose, design an architecture that get the task done. They have a strong dimensionality reduction properties that can be exploited effectively to implement some of these workflows that we have, that it's really not needed to be done in high dimensional spaces. And the parameterization, as I mentioned, exhibit robustness against uncertainty in the geological scenarios while actually capturing some of the complex patterns that we have in these systems. And finally, the latent space representations offer very favorable properties that can be exploited in implementing some of these workflows. With that, I want to thank my lab, especially these 3 members who have really done most of the work, and the sponsors, including Energy Simulation, who have been sponsoring our research for some time now. Thank you so much.
Thank you, Behnam. We have about 5 minutes for questions, so I'd like to encourage questions from the audience. If you can, come down to the microphone. It would be helpful for everyone to hear. Yes, Fahid.
Hi, Behnam. Thank you for an interesting talk. My apologies if my question seems naive because I'm not in this field. So my question is that after you reconstruct the models, how do you test that they are physically consistent with what you should get in the nature?
Right. So we do a lot of validation. That's a very good question. We do a lot of validation. So what I showed you was either the reconstruction results for, let's say, a permeability field, or the corresponding data match. But we actually compare that against the traditional way of doing it, number one. And number two is the models that we produce. If there's a prediction step here in the ENKF, that prediction step we validated against an actual simulator to make sure. And most of the time, it's not perfect, but it's within the range that you would expect it to be. Yeah.
Stefan.
Thanks for this great presentation. I'm not really a machine learning expert, so it might be a naive question. But so your encoder is reducing degrees of freedom. How do you then know how many degrees of freedom in the end you really need in your latent space?
Yeah, that's a very good question here. So a lot of it is really hyperparameter tuning, including that dimensionality. Number of layers, how many nodes do you want to have in each layer? What is the size of the filter? There's a lot of art that goes into designing these kind of architectures. And a lot of it is really experience together with trial and errors to see which one will give you a better performance.
And how does that then influence the amount of calibration or training data or tuning data that you
That's a very good question, because depending on how much data you have, at the end what you're really doing is you're training a large number of weights within this kind of mapping scheme that you have. So if you make this very deep, very high dimensional in terms of the parameters you need to tune, then the data need is going to go up. So there's a combination of data need and sometimes constraints that you can bring. There's a lot of talks about physics-informed, physics-constrained approaches to these kind of architectures, where we are in a field where data doesn't come to us. We collect data which is costly and technically difficult to do in the subsurface environment. So in order to compensate for that, one of the promising research directions is how can you bring domain knowledge, physics, and how can you actually do this, the samples that you choose for training, how can you actually optimize so that you don't...
Can you pre-train? Just using like an image pattern recognition with circles and triangles and like these ResNet and so on, they're all pre-trained, right? With generic data. Can you do that here as well, or is that not so good?
So you can, but depends on what you want to do with that, right? You can, if your goal is to test how you can reduce data needs, of course you can, because the first thing you do, you test to see what is the prediction capability of that model. Now, whether you have circles or squares may not matter that much. It could be different when you go to a real field application where the patterns become very complex. Right? But sure, if you want to look at how to optimize the number of samples that you need, or where to collect the samples, or sure, you can use existing data sets out there. Yeah.
One last quick question. Tisa.
Yeah, thank you. So can you use this method in an iterative way to design data collection strategies like in the future?
Yeah, that's also very good question. In particular for our field, when we look at the kind of data that we have, we are very limited in terms of the coverage that we have for the data. And a lot of these techniques require repeated samples, instances of the samples that you should generate. In this particular case, because I'm using simulated data, part of the optimization we are working on right now is how to minimize the number of samples you need. Basically reducing redundancy in your sampling. However, when you go to a real application where you say you want to design your monitoring system for data collection, then that goes into optimizing the location, let's say, of that data collection based on maximizing the accuracy of your prediction when you're designing these architectures. Definitely, that's one of the actually important research directions moving forward for if we are to use these kind of methods. Because we are limited in data, optimizing what data you collect, where you collect it is very critical.
Excellent. Given the time, we'll close the session. Oh, sorry. Is it a quick question? How about a quick question, quick answer, then we'll move on.
So when you backpropagate, you basically do a gradient descent, and then the question is about the learning rate and how you exactly do it. You can do it in a batch mode so that you collect training data and optimize in.
Yeah, it's done in the batch mode,
yeah.
And we are using basically a typical algorithm like Adam optimizer for that. Nothing really fancy. I think the power of this technique is mostly in the data and the design of the architecture. The existing methods for training are working pretty well. So
there's relatively little sensitivity regarding learning rate you choose, or
when you make this model this type of model a little bit deeper, then you may sometimes encounter like vanishing kind of gradients and issues like that. But there are also techniques available to deal with those.
Thank you.
Yeah.
Okay, with that, please let's thank our speaker one more time for an outstanding talk.